Welcome to Ask and Learn.
Hi everybody, thanks for joining me today. What we're looking at right now is a problem that deals with work and kinetic energy. What we have is a block shown here with an M that is connected to a spring with spring shown in a cable and that is connected to spring B. We're given the mass of the block, the spring constants, which are the same at 2 kilonewtons a meter, and we're asked to find the velocity when the block has been released from rest and has moved down 50 millimeters, and also the maximum velocity of the block. So the first thing we're going to do, as with any problem, is draw a free body diagram, and we're going to draw a free body diagram of the block. So we have the block here, we have the weight force acting down, and we have two spring forces acting on it. We have spring force of Fa, which is pushing up from the bottom, and we also have the spring force Fb, which is pulling it from the top. Now I know we have a cable that is attached to this spring and the block, but due to Newton's third law and forces that are equal to each other, that are equal and opposite, we can forego the tension and just say that tension is equal to the spring force, which is what we have done here. We are going to consider the down direction our positive, since we're assuming that is the direction that the block first moves in. So using our kinetic energy and work relations, we know that the initial kinetic energy is 0 because the system is starting from rest, and we know that T2 is simply 1/2 mv squared, and that is the kinetic energy of the block. So what we're going to do now is we are going to develop an expression for our work. So work from 1 to 2, there are 3 forces at play here. So the first is the weight, which is acting in the direction of motion, so that is going to be positive work. So we're just going to call that W times XA. Then we have the negative work due to the spring, spring A. So that's 1/2 Ka XA squared. And then we have negative work from the other spring as well. That is 1/2 Ka x B squared. Now we know that the distance XA is equal, we know that the distance XB is equal to XA over 2. So by plugging that known information in, we get an expression for the work as WXA minus 1/2 Ka XA squared minus 1/2 Kb XA over 2 squared. Remember that we know that Ka and Kb are the same, so from here on out I'm just going to refer to this as K. So utilizing this equation, remember that we are asked to find the velocity of the block when it is moved down 50 millimeters. So our XA in this case is 50 millimeters. Plugging this in to this equation above, remember we know the mass is 10 kilograms, so we know the weight. We know Ka, which is 2 kilonewtons, and we know Kb, which is also 2 kilonewtons, and we know XA, which is 50 millimeters. So here, from plugging those quantities in, we get the work is equal to 1.78 joules. Now using our kinetic energy and work relation, we know that T1 plus U1 to 2 is equal to T2. The system is starting from rest, so T1 is equal to 0. So we just have U12 is equal to T2, which we know is equal to 1/2 mv squared. Solving for V, we get 2 times U1 to 2 all over the mass, and the square root is equal to our answer, and our final answer is 0.56 meters per second. 0.59 meters per second. And that's our final answer. Remember, we're also now asked to solve for the maximum velocity. So we're going to use the same relation as before, that the kinetic energy plus the work is equal to the final kinetic energy. So let me rewrite that. So T1 plus U1 to 2 equals T2. Remember, we're starting from rest. So T1 is actually equal to 0. So we're left with the same relation as before. And now for U1 to 2, we're just going to do this solely in terms of variables. So that'll be W times X. So the work done by the weight force minus the work done by one spring minus the work done by the spring on the top. So as you can see, we can combine some of these like terms, and we end with an expression that is Wx minus 5 over 8 kx squared. So now we have an expression to solve for kinetic energy. So we have that T2 equals 1/2 mv squared, which is equal to this expression for the work, Wx minus 5x kx squared. So we're asked to solve for maximum velocity. Obviously, it's a little difficult to do that directly because we have a velocity squared term, but we know that if we maximize kinetic energy, we are inherently maximizing the velocity because the mass is the same. So what we're going to do is we're going to take the derivative of kinetic energy, so the derivative of T2 with respect to x, to solve for the position at which we have the maximum velocity. So this gives us weight minus 5 over 4 kx. Solving for x, we get an x of 4 mg over 5k, and this is the position at which we have the greatest kinetic energy. So using this x value that we have here, we can plug this into the equation for kinetic energy and work to solve for our velocity. So recalling our kinetic energy relation, we have 1/2 mv squared equals Wx minus 5 over 8 kx squared. Now if we plug in this x for everywhere that we see x, we get a relation that we can solve for, and we can solve for v. So plugging those values in, we solve for v max to be 0.62 meters per second. And that is our final answer.